Hello, I'm Cyril Naves, doctoral student. Today, I would like to present our work, Automotive Data Certification Problem, a view on effective blockchain architectural solution. This work was done along with Severine Glock, David Bercovitz, Patricia Guitton of Renault Software Labs, and Professor François Verdier of Université Côte d'Azur. These are a list of topics that we would like to present today. Automated theft problem, architectural design, non-wallet architecture, and wallet architecture. These are the proposed architectures. And functional and performance evaluation done on the architecture. And finally, we would like to conclude our work. First, the automated theft problem. Looking at the automated theft problem, the basis of this is the cars. Cars today are more of have turned more from mere mechanical machine to more of a connected device. In this case, a fourth industrial revolution, we see cars more of a gadget than of a mere machine which runs on the road. It is able to communicate with external systems. It is able to communicate with external cars as well as have a peer-to-peer communication with each of the cars, transmitting the traffic data, transmitting the road conditions, transmitting the localization conditions, etc. And also it's able to get some real-time information based on weather, etc. from other sources. The car has been able to interact with various partners. It is able to create synergies between various actors around it. So in this stage, we would like to address one of the basic problems of an automotive industry is data certification. How do we certify that the data which comes out of the car and the data which it receives is legible, is genuine, and it can be trusted as well. And also with the car data which it sends out is also a trusted and validated data. So there are many use cases which pertain to data certification, but we would like to concentrate on just one of the use cases, which is basically car clocking or automated theft problem. Basically, in before days, we were able to do it mechanically. Now, with the age of digital odometers, we are able to do it with manipulating the electronic devices, and then we are able to change or clock the odometer in order to gain some economic benefits out of it. This has been a serious concern because it's not only with data certification issue, it's also a credibility issue. For example, nowadays OEM manufacturers have focused more on second-hand reselling of cars. So in this case, we see a $2,000 billion market, especially only with second-hand connected cars. We also see more of the credibility issue with respect to the cars in this case, because looking at if the history of the car or the odometer kilometers it has run on the road can be changed, then it really affects the price of the car. And also we see automated theft happening very predominantly in almost all the countries. And according to European Parliament, in one of their articles, they have mentioned that around $6 to $9 billion of losses have been reported due to odometer theft. So this is one of the serious issues, and many automotive companies are focusing on this issue to address this issue. Yeah, and also in order to address the automated problem, there have been various centralized solutions, one of which is proposed by the French government. For example, in this case, it gives you the whole historical data of the car, for example, all this data of purchase, data of registration, etc., all about its accident details, etc. These data is more of centralized in this case, is more of the verifiability data is certainly a lacking feature. And this is why we move to more decentralized system where various participants who can participate and validate the data and could give us the cross verification, which is certainly lacking in this case of, even though it's government owned, but certainly the benefit with decentralized systems. The architectural design that we would like to present to you is based on certain decisions that we made initially. With regard to the design decision, the first design decision, basically we have public, private, and consortium partners. The problem with public is more of open, and also the latency is more because no number of participants can be in the network, and the transaction is constant in terms of crypto money, and there's scalability with more number of partners, and there's also privacy concern. In case of private, it's too closed, and the reliability of data is certainly a question mark, and there is no transaction cost. There is a particular infrastructure cost because more private. But in terms of consortium, it's more balanced between multiple participants in the ecosystem. It can be a shared infrastructure, and also the privacy can be addressed because the privacy is more of a consortium level of partners with a level of agreement, and there's no transaction cost associated with it. The second design decision was to choose between embedded node as well as light node and just make an API transaction. The problem with embedded node was basically it had network issues, and also the data was humongously stored on the vehicle, which is not acceptable, and also the computation energy cost is more if you store the data on the vehicle. And second, in case of light node, it just stores a Merkle tree, but also it cannot be stored inside the vehicle. It can be stored on the cloud storage along with the other full nodes. And also the vehicle can at least at minimum can do an API transaction on the network, which will be much convenient, and also it can be within acceptable limits, and also the computation energy cost will be much lower. The third design decision that we would like to present to you is the type of blockchain that we have implemented on. It's basically Ethereum. Ethereum is very well known for being a public blockchain, and it's very well known for its cryptocurrency networks, but it can also be used in the private blockchain context. And it has more power in developing distributed applications because it has a smart contract layer. And also the type of algorithm, the consensus algorithm you have chosen for this one is proof of authority, because proof of authority is very much lighter compared to proof of work. And the type of block creation in the proof of authority is much faster, and also it's much more scalable than in case of proof of work. And also there is a time parameter that we can choose and how fast we can create blocks in the network. This basically creates, in case of private participants or very well-known verified participants, one can use proof of authority compared to proof of work. Proof of work, because proof of work is more applicable in case of public networks. And also the smart contract gives us much more powerful features in order to write a well distributed app applications where we have multiple actors in our ecosystem. So yeah. So the third most important thing that you'd like to discuss is the non-wallet architecture. The non-wallet architecture is a preliminary architecture from where we develop our wallet architecture as well. So the primary use case of non-wallet architecture is first, there is a network, the blockchain network, which is created, it's a consortium network, which is comprised of participants like from various OEMs and government partners. And the blockchain contains the smart contract, which stores the hash of the data, and also hash of the data, basically the hash of the data for against each vehicle in a time bound manner. And then what happens in this case is basically the vehicle, when it completes a journey or a trajectory, it gets two sources of data. Basically, the two sources of data are the contextual data. We can term it as contextual data. One is the odometer value, the actual raw odometer values, and the second is case of GPS data. What we do, the internal validation is, in this case, like we would like to do, is basically we need to cross-validate the data of the odometer against the GPS coordinates. So using the GPS coordinates, we can calculate the total distance covered by the vehicle. And once this internal validation is done, then the vehicle is eligible for sending a smart contract transaction. Smart contract transaction will hash all the data of all the contextual data, and then it will calculate the hash, and then it will send the hash towards the smart contract, which is stored on the blockchain. And also, simultaneously, it sends the raw data, the encrypted raw data, to the database, which is maintained by each OEM. For example, each OEM considering the vehicle who manufactured that particular vehicle. They maintain the database, encrypted database, and then finally, when the owner desires a certification, then he can get the encrypted data decrypted, and then the OEM can also recalculate the hash and verify the hash against the smart contract stored hash, and then give the proper certification that this car has traveled so many odometer kilometers. We focus on the wallet architecture, which is an improvised version of the non-wallet architecture. In wallet architecture, the odometer kilometer is represented in terms of odometer tokens. Basically, we create a network which is comprised of two sets of actors, non-admins and admins. The admins are basically the OEM actors as well as the government actors. And then we have the non-admins, which are basically the vehicles which participate in the network. These vehicles will have their own wallet, which is present on the network. And this wallet will be funded with odometer tokens as soon as they complete the requisite number of kilometers. Basically, it will be subjected to a consensus And then after the consensus among the admin nodes is fulfilled, and then the odometer token balance is incremented for the corresponding vehicle wallet. So in order for the vehicle to join the network also at first, it also needs to place a requisition onto the network, and then the OEM nodes or the admin nodes to undergo a consensus for this new transaction or the transaction, and then they accept the new vehicle to join the network. This is achieved by three contracts which are deployed on the network in the consortium network, through which through which we create this token economy using three contracts which are deployed on the network. Basically, the wallet contract, the transaction contract, and the main contract. The wallet contract takes into the decision control of the odometer economy, the creation of the tokens, the deposition of the tokens, and basically also the wallet balance of each of the vehicle. The transaction contract takes into account the type of transactions which can be accommodated inside the network. Basically, it can be an authentication transaction, authorization transaction, or it can be the token requisition transaction. This type of functionalities are covered under the transaction contract. And then the main contract, basically it acts as an orchestration layer between the transaction contract and the wallet contract. So there is a consensus happening inside the contract level also, which we call it inter-token economy, smart contract orchestrated consensus. This consensus is an additional to the existing consensus proof of authority which exists at the network layer. So there's two levels of consensus happening. This is done in order to audit the type of transactions which enter the network and the type of transactions which get validated and get approved. This is an additional. So after the creation of the network, basically of the three smart contract, then the creating of the consensus layer, the smart contract layer, and then the vehicle, in order after its manufacturing, in order to be on roads, it has to enter the network. So the initial process is basically getting authentication and authorization done for getting the appropriate permission to get the tokens and to register itself inside the network. So the initial transaction will be to join the network. Then when this vehicle emits, it's then approved by all its OEMs and all the other OEM partners. And then when this is validated, then the vehicle is able to join the network as a non-admin node. Once after completing the journey, then it's able to request for the tokens. This request for tokens comprises of two phases. Basically, the first validation is internal validation. The internal validation is similar in terms to the non-wallet architecture, like in cross comparison of the GPS values and the odometer values. This cross validation of data is done, and then the vehicle, when it has to access for more tokens in terms of the odometer kilometers, it has to make a request, and the request is then validated. Basically, the request has to be an addition over the existing balance. So this validation is done, and then the vehicle can make a request to the main contract. The main contract then takes it forward, then creates a new transaction in the network. The new transaction in the network then is subjected to a consensus among the admin nodes. After this consensus is accepted, then the vote majority is garnered for this transaction. Then the token balance is incremented for the vehicle. So depending on the type of transaction, we have a vote majority needed. The vote majority needed, the vote majority needed can also be set dynamically inside the network, because we have to differentiate the transactions, because the authentication transaction is very much important, because no node can at will leave or join the network. And also the request of odometer tokens is more periodical. In this case, it can have a lesser priority. So the vote majority can differ. So we wanted to make it generic. So the vote majority calculated is based on the agreed consensus percentage, as you can find in the right, and also the vote majority needed and the total admin nodes which are present inside the network. So this is calculated based on these parameters. The agreed consensus percentage is what the admin nodes have to agree on to be set inside the network. This is also a type of transaction. This is basically the consensus parameter setting transaction. This which is agreed during the network creation phase. So after this token requisition and token deposition is done, then the OEM or the vehicle can make a request for the certificate of the data which is being represented, the odometer certificate, and then it can retrieve the latest value or the odometer value or the odometer token balance inside the wallet, and then it can deliver a certificate saying that this vehicle has traversed the amount of kilometers. This is basically the entire life. Next, what we do is basically, since we have completed our two architecture discussion, we decided to do functional evaluation of these two architectures and to arrive at the best and to decide the best architecture among these. The two architectures are evaluated functionally by across these different parameters. And these different parameters are basically a mix of both distributed systems and blockchain systems. In blockchain systems, basically like in CAP theorem on distributed systems, we have something known as SSD theorem, or you can call it trilemma, blockchain trilemma, basically the scalability, security, as well as decentralization. So one can achieve two of these three parameters at the same time, like in CAP theorem, or of consistent availability and partition tolerance, like in distributed systems. So we took into all these parameters, and then we decided to measure the various performance of each of the parameters. Basically, in decentralization, we look at how far the nodes and all the nodes can participate inside the network. And in case of wallet architecture, we have the non-admin nodes as well as admin nodes. It's basically a hierarchical level. It's not completely decentralized, a level-based playing field, but we can term it as a quasi-decentralization. So, but in case of non-wallet architecture, the vehicles have no say inside the network. And the second one is latency. Latency is basically the throughput of the throughput in the network of each transactions. So how fast the transactions can be completed inside the network. So basically, in case of wallet, it performs faster because it's only smart contract transactions. It doesn't have another encryption, decryption process also in its workflow. And second, in security level, we have authentication authorization in wallet architecture compared to none in the non-wallet architecture. And scalability, the scalability can be taken in terms of enlarging the network with more number of car nodes or more number of vehicle nodes or more number of OEM nodes. The scalability, in terms of scalability, the wallet architecture performs better because it's mostly a deployment of light nodes, and the light nodes don't affect the scalability in any sense because they don't participate in the block creation process. The next one is the governance phase. The governance phase is more well-defined in case of wallet architecture with a hierarchy level. So it sets the validation process and the audit process inside the network. And privacy, the pseudonymization, as discussed, the pseudonymization of data is already achieved here, but the raw data is directly stored in case of non-wallet architecture, which poses a big security problem as well as a privacy concern. The data validation, the two levels of validation done inside the wallet architecture compared to only one validation inside the non-wallet architecture. And the genericity is basically this architecture can be proposed not only for odometer representation, odometer value representation, but also other numerical data. So the architecture is more generic, but the non-wallet architecture is not very generic. So it performs much better. This can be used for other. It can also be used in the case where we can store multiple data at the same time in the network, multiple different types of tokens. For example, the car health battery, the car health of the battery can be stored as tokens, etc. And next, the infrastructure is minimized because the fundamental aspect of having a decentralized system, or in this case of blockchains, is basically to minimize the infrastructure cost because the cost is shared among its peers. But in case of non-wallet architecture, we have an additional burden of maintaining the database, the key wallet, etc., which had some additional cost and maintenance cost to it. But in terms of wallet architecture, it's much better. So the clear winner among these two architectures is wallet. The wallet architecture is much better compared to non-wallet architecture. So we progress further on the non-wallet architecture's performance. So we decided to do the performance aspect on basically two types of network. One was a local network and one was a cloud network, which is basically Azure nodes. The local network basically was an Intel machine and with 8 GB of RAM and 2 vCPUs. And the cloud one was B2MS, so which is almost average performance, 8 GB of RAM and 2 vCPUs. And in the network, we had 3 admin nodes, basically 3 seeders inside the network, and 3 clients or vehicles which are simulated and which basically from Raspberry Pis, which are sending the the transaction to the blockchain node. And the total amount of transactions we took into account was around 600,000 transactions. And the communication, the API mode of communication was WebSocket based. And this was a simple token request transaction. So we decided to benchmark this transaction basically. The transaction, when you take in terms of Ethereum concept, the transaction accumulates a gas. Gas is basically a representation of calculation complexity or calculation cost. So it's 38,149. So, and we set the block gas in terms of the transaction gas. We set it the ratio of 6,000. Basically, this ratio was identified by part of our earlier work, which is done in order to benchmark EVM as EVM Ethereum in general. So we achieved at a good ratio of 6,000. 6,000 is the ideal block gas limit. So it can accommodate 6,000 transactions inside each block. And the get version, the get is basically the client used inside Ethereum. It was 64-bit client, a version of 1.9.18, which is almost the latest, which is available now, almost the latest. And the Python clients were used to send the transactions from the Raspberry Pi to the centralized blockchain network. So apart from the separation or the type of networks, we also had a type of transaction deposition of the transactions, sending of the transactions. We differed by non-load balanced and load balanced. Non-load balanced is basically one-to-one transactions. We had the Raspberry Pi, which was directly sending the transactions to its OEM nodes. So each one had one-to-one communication. It's a direct communication between the Raspberry Pi and also the light node as well as its vehicle node. Basically one-to-one communication. And the load balanced one was pretty different, because the vehicles or the Raspberry Pis were sending to a load balancer, and the load balancer was then directing the request towards each of the nodes middleware. Each node, or basically each OEM node, had a middleware operating behind its blockchain node. What the middleware did, because when it had a directed request to it, it stored the request inside a queue, and this queue is then operated by a set of threads which are working in the consumer worker model. So when it continuously polls for new requests inside the queue, and then when it finds a new request, it then works on the request, and then it forms the transaction, and then sends the transaction to the blockchain node. So each OEM node had a middleware running on it. So it was working on this, because why we had to do all this additional stuff, because the Ethereum internally has a nonce problem, because the nonce had to be generated in an incremental order. It's because of this we had to deploy a cache inside each middleware to make sure that even if we distribute the queue among multiple threads working parallelly, the nonce was always incremented properly, and there was no duplication of nonce. This was very fundamental requirement inside Ethereum transaction submission. So this is how it was. So we have 4 different aspects to be covered, basically cloud versus local and load balanced versus non-load balanced. So in this case, it's basically the non-load balanced, which is in the local network, which achieves much better transactions per second. Basically, the throughput of the network is much more compared to other types of transactions sending. So basically, why? Because local has a much lesser RTT compared to the Azure network. In Azure network, it was around 1,000, and the RTT for local was around 200. And also in non-load balance, it was basically one-to-one communication between the nodes and with the Raspberry Pis. But it was in load balance. We had a middleware, which is routing, and also we had a routing of the request, and also middleware, which is processing the request. This explains why it has much better transactions per second. So, but even though in the case we have much better in non-load balanced fashion, we choose a load balance because it's much more reliable, because even in the case of failure of node, we have the possibility to recover the transactions stored inside the queue. And here in this load balance architecture, and as well as non-load balance architecture, we perform the scalability test across 3, 7, 11, and 15 nodes. And what we notice is basically we notice a drop, as you see in generally blockchain trilemma. We see a drop in the network performance, but we see some increase in we see some increase in the load balanced fashion. Why? Because since we have more nodes which can handle the transactions at the same time, we see some increase, but we see a drop as well. Because due to the load balanced architecture, how it's architected, we see this increase, but normally in the blockchain we see a normal drop in performance. So we take this best figure of 538 and then we calculate in terms of the number of transactions which can be achieved in each day. This is the amount of transactions which can be achieved in a day, and we consider if if each vehicle completes 4 trips per day, then it can request for 4 token smart contract transactions. So in this case, how many vehicles can be supported inside the network is basically this amount vehicles can be supported inside the network. This is somewhat an acceptable figure based on the load balanced wallet architecture. The conclusion is the positives is basically we have the generic architecture for automotive data certification, and we also respect the privacy concerns. We can roll out multiple tokens for capturing for each type of data representation, but it's limited to numerical data. And then it's an acceptable performance, what we've noticed in the previous slides. The limitations, yes, to numerical data, it cannot store video or audio data. And also the load balanced architecture can be improved a bit further than the 538 which you achieved. And then the IPFS storage can be considered. Thank you very much.